Hello cost accountants, here are some example exercises for chapter 10. In this chapter we're going to be dealing with cost functions. And cost functions are a way to describe mathematically how a cost is expected to change when its level of activity that goes into that cost also changes. So it examines the relationship between activity and cost and makes a formula to help you come up with a budgeted cost you can expect based on a level of activity. And that formula that we're going to use is called the linear regression model. So we're going to take an expected amount of cost, which is our dependent variable, and we're going to estimate a level of activity, which is our independent variable. And by estimating that level of activity and having this formula y hat equals a plus bx filled in, it's going to give us our predicted cost. There are different ways to go about doing this. The quickest, easiest approximation method is the high-low method, and this estimates our slope, which is b, and our y-intercept, which is a, based upon the highest activity observance in the recent data and the lowest observance of activity in our recent data. So instead of going through and taking every single month out of the year, or the last 2 years, etc., we're going to take only the high point and the low point. And because we have less numbers in there, it makes it easier to compute mathematically while still giving you a fairly accurate answer. Here we have an example problem, and in this problem, Horizon Travel offers helicopter service from suburban towns to JFK International Airport in New York City. Each of its 10 helicopters makes between 1,000 and 2,000 round trips per year. The records indicate that if a helicopter makes 1,000 round trips per year, it is going to incur an average operating cost of $350 per round trip. And if a helicopter makes 2,000 round trips per year, it's going to incur an average operating cost of $300 per round trip. First step, we need to figure out what is our x and what is our y. Well, x makes y change. It's the easiest way to figure out what your variables are. We have the number of round trips that happens and the operating cost. Well, what one of those makes the other one change? The more round trips a helicopter makes, the higher its operating cost is going to be. So our x is going to be annual round trips, and y is going to be our annual operating cost. Let's use this high-low method to come up with some kind of cost function where we can make predictions about upcoming operating costs. We need to find our highest observation of x and lowest observation of x in the data. Well, what is our x? It is the number of round trips. I set up this question conveniently, so there's not too much information to parse your way through. It says each helicopter makes between 1,000 and 2,000 round trips, which means our highest observation is going to be the 2,000, and our lowest observation is going to be 1,000. The records indicate that if a helicopter has made 1,000 round trips in the year, it's going to incur an average operating cost of $350 per round trip. So at our lowest observation point, our cost per round trip is going to be $350. Information also tells us that if a helicopter takes 2,000 round trips per year, it's going to incur an average operating cost per trip of $300, which means that our annual operating cost is just going to be found by taking our annual round trips times our cost per trip, 600,000 for the highest observation level, 350,000 for the lowest observation level. So now that we have all our information, essentially what is our highest and lowest value of x and what is our highest and lowest value of y, we can figure out our delta, which is just the difference between the two numbers. The difference between the highest amount of round trips a helicopter makes and the lowest is 1,000, and the difference in annual operating costs from our highest observation and our lowest observation is 250,000. And since we have this information, we can use all of this to figure out our cost function, which we're going to do by taking the least square regression model. First thing we need is to find our b, and b can be found by taking delta y and dividing it by delta x, or in less mathematical terms, taking the difference in annual operating cost between the highest observation point and the lowest observation point and dividing it by the difference in annual round trips between the highest observation point and the lowest observation point. Well, we already have that information, so our change in y, or our delta y, is going to be 250,000. Our change in x is going to be 1,000, which means that our slope is 250. What that means is for each extra trip that a helicopter takes, it is going to increase the annual operating cost of that helicopter by about $250. So with B, we can compute the other variable that we need, which is A. A is our constant. A is how much we have to pay regardless if we take 0 trips or 1,000,000 trips. It's our fixed cost, if you will, related to operations. And we can figure that out by taking Y minus BX. So let's take one of our 2 observation levels, and I'll start with the highest. What was the annual operating cost at our highest observation? It was $600,000. Well, if we subtract from that our slope, which was 250, we just found that, and our activity level at that highest observation point, 200,000, we can determine our y-intercept, or our A, if you will. So 600,000 minus the product of 250 and 2,000 is going to come out to be 100,000. At the lowest observation level, our annual operating cost was 350,000. The slope is still 250, and the activity level at the lowest level of activity observed was 1,000 round trips. So 350,000 minus the product of 250 and 1,000 comes out to be 100,000. This is always going to be true when you're finding your A. The highest observation point and the lowest observation point should always solve to the same exact number of A, so you'll know if you're doing this correctly, if that works out for you. Now we have A, and now we have B, which is convenient because our formula was y hat equals A plus BX. So our predicted annual operating costs are going to be equal to the constant that we have to pay, which is our y-intercept, plus our slope, the increase that we have for each additional unit of X, each additional round trip in this case, times the budgeted amount of round trips that we're going to make. And to set this up mathematically, we know that our A was 100,000 and our B was 250, so we can solve for any budgeted quantity we want to have by taking the formula of y hat equals 100,000 plus 250 times X. So if Regression Travel expects each helicopter to make on average 1,200 round trips in the coming year, what should it estimate its operating budget to be for the helicopter fleet? Well, we have our regression equation, y hat equals 100,000 plus 250 times X. Let's just simply sub in the number of round trips we expect each copter to make for our X. So we have 100,000 plus 250 times 1,200. It's going to come out to be 400,000. But this 400,000 is per helicopter. And we're not asked to find the operating budget for each helicopter. We're asked to find it for the entire fleet. So to find it for the entire fleet, we just multiply it by the size of the fleet, which was 10. We come up with a budget operating cost for the entire fleet of $4 million. For problem 2, let's take a problem that has a little more information to it. Catherine McCarthy, who is the sales manager of Baxter Arenas, is checking to see if there's any relationship between promotional costs and ticket revenues at the sports stadium, and she has the data for each for the last 9 months. So April through December, we have each month's respective amount of ticket revenues that the sports arena made and the amount of promotional costs that Baxter Arenas paid during that month. Well, let's use this information and the high-low method to determine the expected ticket revenues if Baxter Arenas spends $200,000 on promotional costs during January. Again, we got our high-low table. Highest observation of X that we have in here. Well, what is our X? X makes Y change. We're saying that the promotional costs change the amount of ticket revenues that we have. So our highest observation of X is at $197,000 in promotional costs that we spent during December. And the highest observed level of ticket revenues were $751,000. The lowest observation of X we have was the $52,000 in promotional costs that we spent during April. And ticket revenues were the lowest point, $200,000. So our delta, our difference in promotional costs from the cheapest month to the most expensive month was $145,000. And the difference in revenues from the most profitable month to the least profitable month was $551,000. So now we can use that information to figure out our B and our A. Again, B is the change in Y divided by the change in X. In this case, we're going to take 551,000 divided by 145,000, and we're going to come up with $3.80. Now that we have B, we can solve for A. A equals Y minus BX. Well, we throw in our inputs. Our Y, I'm using the highest observation level here for this one, was 751,000. And if we subtract from that the product of 380, our slope, and 197,000, which is our promotional cost at highest observation level, we come up with 2,400. What they're saying here is that if Baxter Arenas did not promote, they would still do $2,400 in ticket sales. So now that we have our A and our B, we can set up Y hat equals A plus BX. And that formula is going to look a little something like this. 2,400 plus 380 times 200,000, which is the promotional cost we are expected to budget for to figure out what our revenues are going to be, coming up to 762,400. So we can go and say that if we spend $200,000 in promotional costs based on our historical data, we should do $762,400 in ticket revenues. And while this works, and it's a good approximation, it's not an exact science. And the reason being is this methodology, the high-low method, is really susceptible to being thrown off, to giving bad data because you had either a really bad month or a really good month. If you want to have more accurate data, you can't just take the highest month and the lowest month and use those. You need to take consideration of all the months, which brings in a lot more complex mathematical calculation. Fortunately for you guys, I'm going to show you how to do it in Excel right now. So here we have our data from April through December for the Baxter Arenas, and we can use Excel to very quickly calculate our expected revenues based on $200,000 in promotional costs, taking into consideration every month and not just the highest method and or highest month and the lowest month. But to do this, we need to install something in Excel which for whatever reason is not installed naturally, and it is a data analysis pack. So let's do this first. And how you do this is you come up and you click File, and then you go down to Options. In Options, it's going to give you a list of stuff on this left hand column of your screen. You want to pick Add-ins. And when you get into Add-ins, it gives you a whole bunch of different things to pick from. The one that we want is this, Analysis Tool Pack VBA. So if you go and you click on that and you hit OK, you should have installed Data Analysis Tool Pack. You can find out if it's there by going to the Data tab on the top, and way over in the top right corner, as we see right here, we should have Data Analysis. So now that we have this installed, how can we use it? Well, let's click on Data Analysis. There's a whole bunch of different statistical methods that you can have in here. There's ANOVA, there's covariance, there is F-test, there's all sorts of crazy things, but the one that we want is regression. So click on regression and hit OK. And when you get in here, it is going to ask you to fill in your Y range and your X range. Well, again, for us, our Y, the thing that is changed by something else, is going to be our ticket revenue. So for our Y range, we just want to highlight all of the different values of Y that we have in our data. For the X range, well, that's going to be all of our promotional costs. So let's go and let's highlight all of the promotional costs we have. So now your Y range should be the entire list of all of your different revenues, and your X range should be the entire list of your different levels of activity. In this case, the amount of promotional expenses that you're putting into generating revenue. And now that we have all of this, we can go and we can hit OK. And when we hit OK, this pops up, the summary output. And there is a whole bunch of statistical information on here. Your degrees of freedom, your coefficient of determination, your standard deviations, blah, 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 blah. What you're concerned with for the purpose of this class are these two numbers right here. Where it says intercept, and go and change the color for you right there. That is the constant. That is how much you would have to pay at zero level of activity. That is our A. Down here where it says X variable 1, this is the change in Y every time X changes by 1. Well, guess what that is? That is our slope. And since it's our slope, we can call that our B. So A right here, B right here, and with that we can go and we can get our answer. See, what they're asking us for is the expected January revenues based on $200,000 in promotional costs. So we can take y equals a plus bx and solve this. So on the cell we can hit equals a plus b times our x. And our x given in the problem that we just figured out before is what happens if we have $200,000 in promotional costs. So we can just type in 200,000 up on the top, zoom in on that bar for you guys a little bit, and we just go and we hit enter. And according to our regression equation, the expected January revenues based on $200,000 in promotional costs will be $773,984.25. So this is really close to what we came up with the high-low method, which was 762,400, but it's a more accurate means, and it's really close because the data doesn't have anything crazy in it. It's a pretty consistent increase between ticket revenues and promotional costs each period. Like I said, if you have 1 month where for whatever reason something happens in life where people don't go to arenas and you have really bad ticket revenues even though you paid a lot of promotional costs, that's going to throw your data off. So this is a more accurate way of doing things.